Proteases. What is proteases? The proteases, also known as peptidases or proteinases, are enzymes that break down protein by hydrolyzing peptide bonds, producing smaller peptides and amino acids. This function is essentially in many biological processes and is widely applied in industries that require controlled protein degradation. According to the International Union of Biochemistry and Molecular Biology, proteases are classified under EC number 3.4, placing them in the group of peptide hydrolases. Based on their site of action, proteases can be divided into exopeptidase, which acts on the ends of polypeptide chains, or endopeptidase, which cleave peptide bonds within the protein source. Proteases are also classified by their catalytic mechanism, including serine, cysteine, aspartic, and metalloproteases. In terms of operating conditions, proteases show different optimal pH ranges. For example, acidic proteases function best between pH 2 and pH 6, neutral proteases between pH 6 and 8, and alkaline proteases at value of pH more than 8. Other than that, most proteins have optimal temperature between 50 and 70 degrees Celsius, although some microbial proteases remain stable and active even at higher temperatures.
Proteases are highly versatile enzymes with wide-ranging industrial applications. In the food industry, proteases-mediated processing increases protein yield and enables the valorization of food byproducts, helping to minimize raw material waste. They also provide a sustainable alternative to chemical cross-linking and depolymerization processes. For decades, exogenous proteases have been established as essential tools in food processing, supporting more sustainable production practices aligned with SDG 12. So why do we need to break down proteins in food processing? Controlled protein hydrolysis improves digestibility, modifies food texture, enhances flavor development, and increases processing efficiency and yield. General protease use involve raw food material preparation, pre-treatment, addition of protease, protein breakdown, controlled enzymatic hydrolysis under controlled conditions, enzyme inactivation, and production of final food product. Proteases function under a wide range of operating conditions. Industrial proteases remain active between 4 to 70 degrees Celsius, with plant proteases showing superior thermal stability. Engineered proteases can operate across pH 2 to 12, while plant proteases typically perform best at alkaline pH, and animal proteases under acidic conditions. Their substrate specificity allows selective modification of food proteins depending on the enzyme source. The accompanying table summarizes common food processes, the proteases used, their sources, and their specific actions, adapted from Dway and Chaudhry 2023. Proteases are extensively applied across multiple sectors of the food industry, such as in the dairy industry, meat industry, baking industry, brewing and beverage industry, seafood processing, in soy and plant-based foods processing, and finally, in infant and medical foods. Benefits of protease in food industry includes increased yield, quality improvements, and reduced cost and energy. However, the use of protease in food industry has its limitations, such as limited stability, risk of overhydrolysis, inhibition effects by salts and metal ions, and worker safety concerns.
Leather processing, proteases act as a biological precision tool. During unhairing and bathing, they specifically degrade hair root protein and non-collagenous fibers without damaging the leather structure. Operating at an alkaline pH, this technique replaces toxic sodium sulfite, reducing wastewater pollution by 60%, and it is cleaner and safer way to produce high-quality, soft leather while supporting SDG 12 through waste valorization. For textiles, proteases serve as a biological scalpel. In silk degumming, they remove the gummy's ricin layer to reveal a natural luster, while in wool, they smooth surface scales to prevent shrinking. By operating at 50 degrees Celsius instead of boiling, we save massive amount of energy and eliminate harsh soda ash. While we must manage worker safety through granulated enzymes, the move to these biodegradable catalysts ensure a greener manufacturing chain. Finally, in pharmaceuticals, proteases like TPA provide life-saving thrombolytic therapy by dissolving blood clots with high specificity. Beyond the clinic, enzymatic biocatalysis allows us to manufacture drugs under mild condition, replacing toxic organic solvent with green chemistry. Despite limitation in enzyme stability, advancements like PE-gelation are enhancing safety and sustainability in medicine. From fashion to medicine, proteases are the key to transitioning from persistent chemical contaminants to sustainable bio-based economy.
Next, I will talk about the application of protease enzymes in environmental cleanup, also known as bioremediation. Proteases are enzymes that break down proteins into smaller peptides and amino acids. In environmental context, they are especially useful for treating protein-rich pollutants found in industrial wastewater, agricultural runoff, and contaminated soils. Proteases are used in environmental cleanup for several reasons. First, they work under mild conditions, meaning lower temperatures and neutral or slightly alkaline pH, which reduces energy consumption. Second, they are highly specific, targeting organic pollutants without generating toxic byproducts. Compared to chemical treatments, protease-based remediation is more eco-friendly, cost-effective, and sustainable. In a typical cleanup process, protease-producing microorganisms such as Bacillus or Pseudomonas are first identified and cultivated. The enzymes are then produced through fermentation and applied directly to polluted water or soil. Proteases hydrolyze complex proteinaceous waste into simpler compounds, which can then be further degraded by naturally occurring microbes. This microbial synergy speeds up the overall biodegradation process. The protease activity is affected by temperature, substrate concentration, immobilization techniques, presence of metal ions, and also pH. The benefits include reduced biochemical oxygen demand, improved water and soil quality, and lower operational costs. For example, protease-treated wastewater shows significant reductions in sludge and organic load. However, there are some limitations. Proteases can lose activity under extreme pH or in the presence of heavy metals, and large-scale environmental application requires proper regulation to ensure ecological safety. Overall, proteases offer a promising green technology for environmental cleanup and strongly support sustainable waste management under SDG 12.
For my part, I will discuss protease enzymes in terms of sustainability and ethics. The application of protease enzymes in industrial processes reflects a shift towards more sustainable and ethically responsible practices. By replacing or reducing harsh chemical treatments, proteases help lower environmental pollution, improve waste management, and create safer working conditions. Their biodegradable nature and ability to function under mild temperatures and pH also contribute to energy savings and resource conservation. In terms of environmental impact, proteases act as eco-friendly alternatives in industries such as detergents and leather processing. They reduce environmental toxicity and support sustainable waste valorization by converting protein-rich byproducts into useful materials like peptides and amino acids. Proteases also play a role in bioremediation, where they help reduce biochemical oxygen demand in industrial effluents. From a safety perspective, proteases are generally safe when properly formulated in consumer products. However, in industrial settings, exposure to enzyme dust can cause irritation or respiratory sensitization. Therefore, the use of protective equipment and safer formulations such as encapsulated or liquid enzymes is important to protect workers. Regarding waste handling, proteases are effective in degrading protein-rich waste from food processing, leather, and slaughterhouse industries. This reduces COD and BOD levels and supports circular bioeconomy approaches by transforming waste into fertilizers or raw materials for other bioprocesses. Finally, greener improvements include producing proteases using waste substrates and applying genetic engineering or immobilization techniques to improve enzyme efficiency and usability. Overall, protease enzymes align well with SDG goals by promoting responsible production and environmental protection.